All right, so today we have lesson one, reason quantitatively. Today we're going to take a look at three different ways to model real life situations using three different functions. So the first one we're going to look at is our piecewise linear function. So as you can see, we have a graph down here and it's made up of many different line segments. Some of them are increasing, some of them are remaining horizontal. We have decreasing line segments as well. So I'm going to go through, read what the lesson has here, and then kind of explain little bits and pieces where needed. So it starts with some real world events can be represented by graphs of straight lines on a coordinate plane. However, in the real world, not all graphs are straight lines. Many graphs of real world phenomena are curves or combinations of lines and curves. When you encounter these graphs, it is important to know how to interpret them. Usually, the intercepts, maxima, minima, rate of change, domain, and range provide valuable information about the graph and the real-world situation that it represents. So some of those words should definitely be familiar to you so far this year. We just finished talking about domain and ranges and intercepts, and we've talked about maximum and minimum points, and a little bit about rate of change as well. So here we have a piecewise linear function, and this is going to model Mr. Wagner's morning. So if you take a look on the y-axis here, we have the height above the ground in feet, and on the x-axis you have the time. So from about 9 a.m. to noon, we see that there's data points for Mr. Wagner, and then his height above the ground in feet. All right, sorry about that, interrupted there. All right, so let's take a look at this graph here. So we have Mr. Wagner's morning. So he starts from 9, and then this hour is broken up into 4 parts. So from 9 to 9:15, he's traveling up the building. He goes from 0 feet up to 60 feet, and then he remains there for about 15 minutes. Then at 9:30, down to 9:45, he travels down those 60 feet back down to the floor or ground level. Then from 9:45 all the way up to, or from 9:45 to 10 a.m., he's traveling up at a fast rate up to 80 feet, and then kind of at a little bit slower rate continues up all the way up to 140 feet, where he stops and again spends 15 minutes somewhere. Then at, looks like we have 10, 15, 30. At 10:30 to 10:45, he's traveling straight down there from 140 feet down to 0 feet, waits down there, and then again at 11, travels up not quite as high to 120 feet, and slowly works his way back down over the next hour, back down to the floor at noon. So even though this graph is made up of straight line segments, the function is called a piecewise linear function, and it's considered nonlinear. So this type of nonlinear function is called a piecewise linear function, since different line segments or pieces are defined over the entire interval. The graph of a linear function is always just a single straight line. So when we're defining this is a piecewise linear function, right, which is a group of different lines that are different line segments over the course of the domain of this graph here. So if we take a look, they pointed some things out here. They said here is some of the information that the graph shows about Mr. Wagner's morning. One, Mr. Wagner was at his greatest height above the ground between 10:15 and 10:30. So if we take a look at that, the greatest height above the ground was right here, and it was over the interval of 10:15 to 10:30. And at that time, during these 15 minutes, he was 140 feet above the ground. So this is an interpretation of the maxima, right? So the greatest value of the graph. Then if we continue here, it says during the morning, Mr. Wagner was always between 0 and 140 feet above the ground, and this is an interpretation of the range or the spread of the graph, right? This is also our y values for which this graph is defined. So if we were to write the range before, when we were talking about certain functions, we wrote it as an inequality, and that could look something like this, where we have 0 is less than or equal to y, which is less than or equal to 140 feet, right? So this would also show the range of this graph here. And lastly, Mr. Wagner went downstairs the fastest between 10:30 and 10:45. So this is an interpretation of the rate of change or the slope of the graph. So if we take a look from 10:30 to 10:45, that rate of change there, right, which is the change in y's over the change in x's, was the greatest. So if we take a look in the change in y, he went down 140 feet while only going over 15 minutes here on our graph here. So that would have been the rate of change or the slope of this segment of the piecewise function. Now we're going to go on to the next page, page 9. So sometimes you will need to interpret a situation visually in order to sketch a piecewise function graph. Choose the appropriate units and scales on the coordinates of the graph is a key part of interpreting this situation. So making sure that you're using the most of the graph is important to see what's really happening. So this sample question: a boat travels at a constant rate of 16 miles per hour for 3 hours before stopping for 2 hours. So I'm going to highlight our rate of 16 miles per hour, and then also highlight in a different color our time here that we have for 3 hours before stopping for 2 hours. So if it's traveling at a constant rate of 16 miles per hour for 3 hours, then stops for 2 hours, during this 2 hours, we know that it will be traveling at 0 miles per hour. So I'm going to put a little note here for myself, 0 miles per hour. Then the boat continues traveling at a constant rate of 12 miles per hour. And it doesn't tell us really when this boat stops, so we're going to have to say that it just keeps going to the edge of wherever our graph will be. So first step here is to take a look at our graph, and we want to sketch down our axes, and we want to create an appropriate scale. So on our x-axis here, we have time, which will be in hours. And then on our y-axis, we have distance, which is in miles. Now, so far we know that we have at least 3 hours plus 2 hours, which gives us 5 hours that we need to talk about. And then we know that it also needs to continue after that 5 hours. So first we want to count how many squares we have here on our x-axis to determine what we're going to use to count by here. So we have 1, 2, 3, 4, 5, 6, 7, 8. So since we need 5 to start, we're just going to say each one is just 1 hour. So 1 hour, 2, 3, 4, 5, 6, 7, and 8. And then in distances. So the distances that we know it's going to go 16 miles per hour for the first 3 hours. So if we were to calculate how many miles that is, we would just multiply 16 times 3, and we'd get 48. So we know that it's going to travel for 48 miles here, then it stops, and then for the last 3 hours, it's going to travel at 12 miles per hour. So what we can do is add to that 12 times 3, which is 36. So we know that our graph has to be at least 84 miles high. What I would say is let's go through and count by something that is in common between 16 and 12 here. So you could pick a number, say, well, first let's see how many boxes we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 boxes. So in order to keep it kind of something we can work with, let's start with, because we have 16 miles per hour to start with, let's start with a factor of 16 here, and let's count by 8s here. So if we go through, we'll count by 8. So 8, 16, 24, 32, 40, 48, and we keep counting up, 56, 64, 72, 80, 88, 96, 104, and I'm just going to stop there. So for the first 3 hours, it's traveling at a rate of 16 miles per hour, which means that every time, so when we have 16 miles per hour, that means that for each 1 hour we go to the right, we're going to have to go up 16, right? So our slope is 16 over 1. So we're going to go up 16 over 1, put a point. Up 16 again, over 1, put a point. Up 16, and put a point. At this point, we can connect these 3 dots back to our origin. And we have our first segment of the piecewise function. Then for the next 2 hours, they stopped. So if they stopped, they didn't travel anywhere. So we continue here. So here's 1 hour stopped, 2 hours stopped. So we can draw our line. And then the last part, they went at a rate of 12 miles per hour. So 12 miles per hour means we go up 12 while we go over 1. So starting here, we'll try and go up 12. So when we go up 8, that's going up. Then we have to go up another 4, which would be half of this box. We can put a point. Then we go up another 1.5. Then up another 1.5. to get 12 there. And then this is going to be our graph that we have here to model this function here. We can also put an arrow at the end of our line that's going up at 12 miles per hour because we're not given a time frame as to how long that lasted. So if you take a look and read this part down here kind of on your own here, you can pause, but this is exactly what we just did here. So take some time, read through it. If there's any questions that you had as we were going through it, hopefully they'll be explained here. All right, so a second type of nonlinear function is a quadratic function. These functions have a variable term that is squared or raised to the second power. Given an equation of a quadratic function, you can make a table of values that can be plotted on a coordinate plane to form the graph of the function. So here's a sample question here. It says a company markets a new cell phone accessory. The function p is equal to negative 50d squared plus 1,500d is used to predict the total monthly profit of an accessory priced at $D. Sketch a graph that models this function. So start again, highlight the function just so we stands out as to what we're working with here. Then we have to label our axes here. So the variable that is squared is always going to be part of our domain here. So here we have on the domain will be the dollars, right? And here we're talking about the price. So we get a price in dollars. And then on the y-axis here, this function represents the profit. So on the y-axis, we'll have the profit. Now, the first step when we're graphing this is to create a table. So I believe most of you have access now to the calculator through the update on the new computers. If you don't, right, you can follow along and take a look at this one here. So I'm going to start by putting in our function. So on your calculator, you have f of x or f1 of x. That's going to be the same as the variable p here. So we're just going to put in everything after the equal sign. So it should be negative 50. Then here, instead of using d, we're going to use x, negative 50x squared, then plus 1,500, and again, instead of d, we're going to write x, and we'll hit enter. So on your graph, you can't really see anything if you take a look here, so we have to adjust the window here. So in order to adjust the window, we hit menu, window, which is choice 4. Then here, window settings, choice 1. Now, our x minimum, if we take a look at the graph that they gave us here, they do not have any quadrant outside of the first quadrant of our graph here. So our x minimum, we can actually make 0. And then our x max, we're going to follow what they have on the graph below and write our x max as 40. And then again, with the y minimum, we can have a 0. And then the y max, if we take a look, they have it in thousands. So they have 12,000 as their top. So let's also make that our maximum here, 12,000. Then we hit enter, and we take a look at a graph that looks something like that. Now, while this gives us an idea what it looks like, it doesn't necessarily help us graph it. So in order to graph it, we're going to go to Control T for our table here. Now, when you're trying to find the table here, we're looking at our graph, and we're trying to find where the vertex is, right? So where our graph starts to repeat. If we take a look here, between 13, 14, 15, 16, 17, we have this middle number here, which looks like that's going to be our vertex for our graph. So that is at x equals to $15. So I'm going to create my table now on the side here. So we have our dollars and then our profits. This is also like our x's and our y's. If we start, we want to put 15 kind of in the middle here. And at 15, it's $11,250. And then we want to go, we'll count by 5. So let's start at 0. So at 0, it's 0. Then we'll do 5 and 10. At 5, it's 6,250. Then we go down. At 10, it's 10,000. And then we have 15 again. So then we look at 20. So we want our quadratic to start to repeat itself again. So we have 10,000. Then we have 25 and 30. At 25, we should see that's the same as what it was at 5. So it's 6,250. Then at 30, we should expect that it will be 0, which it is, which is great. So when we take a look on the bottom here, price in dollars, now we're going to graph. The price in dollars goes from 0 to $30. So we want to break this into segments that can get us all of these data points here. So we count how many boxes we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 boxes. I think a good... All right, so the way that we should count here is we've got 12 boxes and we want to have it cover our x values all the way up to 30. If we count every other box as 5, then we can have a nice spread out graph here. So we count 1, 2, we have 5, then 10, 15, 20, 25, and 30. And then counting up, we have our profits. If we count each one as 1,000, that should cover our y-axis that has to go all the way up to 11,250. So again, we count 1,000. Then we have 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000, 11,000, and 12,000. Now we can plot our points. So our first one is 0, 0. Then at 5, we go up to 6,000. Then 250, which is about a quarter of the way up. 10, we go up to 10,000. 15, we go up to 11,250, which is again just going to be a little bit over 11. And then we're going to start to repeat ourselves as we come back down here. So at 20, we're at 10,000. At 25, we're at 6,250. And at 30, we're back at 0. Now when we draw this, we draw it in a nice arc to it. And back down. So the quadratic function is increasing. Then it starts to slow down, increasing, reaches its top point here. Right? This is our maximum. This is also our vertex. And then it slowly starts to decrease as it goes down to $30 there. So what this is modeling is it's saying that the amount of money that they'll make is based on the price that they sell their accessory for. So the optimal price, 15, would give them the highest profit. As they start to raise their price to 30, their profits start to go down, and that would be because people weren't buying their accessory, right? But while the price for the accessory is low, like $5, people were buying it, but they weren't making as much money. So if you were this company, you would want to look at $15 as your price, and then you'd make the most money here. So another example of a quadratic function here, and one that you see a lot, is dropping of a ball off of a building. So if we take a look here, Layla dropped a ball from a height of 64 feet. I'm not sure why everyone always wants to drop things off of buildings, but it can be modeled here by this quadratic function. So this graph shows the relationship between the height of the ball and the time it took for the ball to land on the ground. So one thing to note is that when we hit the height of 0, that's when it landed on the ground. You'll often see questions that kind of ask, when did it hit the ground? There we go, we're looking for a height of 0. This one, however, is looking for the approximate rate the ball traveled in miles per hour between half a second, so if we look half a second right here, and 1 second, which is right here. So if we're looking for the rate, and if you take a look at all of these answers, they all have miles per hour. So we're going to have to calculate that by looking in the change of miles. So you'll see we use a triangle. Often we'll use a triangle or delta for change of miles over change of time. Now, we have a couple things going on here. This problem is a little bit unnecessarily difficult just to get us started right away because they didn't give us miles and they didn't give us time in hours, but our answer has to be in miles per hour. So what we're going to do first is write it as the change in feet per second. And then if you can see down here, they showed how to calculate and turn it into miles per hour. So the feet per second would be the change in the y's. So if we take a look here, we're counting by 4. So this has a y value of 60, and this has a y value of 48 here. So if we take a look at the change in that y value here over a half a second would be 60 minus 48 over, and then we're saying we went from 1/2 second to 1 second. So it's a change of 1/2 of a second there. So here we are changing 12 feet in 1/2 a second. And if we get rid of this fraction in the bottom here, or divide 12 divided by 1/2, you'll see that we travel 24 feet in 1 second. Then taking a look, that puts us right here. If we're going to change it to miles per hour, we need to make sure that we are multiplying by 1 mile, which is 5,280 feet. Then also by how many seconds are in 1 hour. So to find how many seconds are in 1 hour, you start with how many seconds are in 1 minute, which would be 60. And then how many minutes are in 1 hour, which is 60. Multiply those together to get 3,600 seconds. Then as we're going through here, you see the units as they cancel out, leaves us with the units we want at miles per hour. Then when you work this out here, we get that it is 16.36, or approximately 16 miles per hour, which is choice B. The last type of function we're going to take a look at is exponential functions. So we have been working a lot with these lately, so these should look familiar. So another type of nonlinear function is an exponential function. These functions have exponents that are variables. An example of an exponential function is y equals 4 to the x. One common exponential function deals with compound interest. To compute compound interest, factors such as the original dollar amount invested, P, the rate, the interest rate, R, and the amount of the interest that is made, T, should be known. The amount of time the interest is made, T, should be known. This is our formula here, A equals P, parentheses, 1 plus R to the T, where A is the balance including the interest. Right? Another exponential function that we have really started working a lot with was f of x equals a b to the x here, right? Where a is our number that we start with, or the amount we start with, and b is our rate of change. This is very similar here, right? So a is how much, or p is how much we start with here. And then when we add 1 plus the rate, we get whatever our b value would be right here. And it's still to an exponent, or it's still to a variable, which is t in this case for compound interest. So if we take a look at this question here, we're basically just going to use that formula that they gave us there, right? Which was that a equals p times 1 plus our rate to our time. So we take a look. Brad puts $800 into a savings account that earns 3% interest compound annually. He does not add any more to this account. Brad will sketch a graph to show the dollar amount in this account for the first 5 years. What dollar amount will be in the savings account in 5 years? Round the amount to the nearest dollar. So if we take a look, they just went through here and took the formula. A equals, right, P parentheses 1 plus R to the T, and substituted in the different variables. So the principal, the amount he started with here, right, was $800. So our $800 goes in the front here. Then it earns 3% interest. So 3% interest, and that part goes right here. Now if you notice, that number is not a 3 because we have to change the percent to a decimal. So to do that, we take 3, right, percent, and we divide by 100, and we get 0.03, which is the number that goes into our formula there. And then finally, we have 5 years, which goes up as our exponent. When you put this into your calculator, right, and work it out, we get that it is about $927.42 in the 5 years. So that $800 at 3% interest turned into $927.42 over 5 years there. So now what we want you to do is go through these next practice problems here, right, and read each problem and then circle the best answer. So the first one here says, from a stop position, a car sped up gradually until it reached a constant speed, and then a car stopped suddenly. Which graph represents the situation? So make sure to take a look at the x and y axis with speed and time. Now would be a good time to pause this video here and give yourself an answer. Circle it in your book if you have it, or write it down, because this will be one of the questions that we want you to input on the quiz that is posted on Schoology. All right, then the next one here says, the function below models the population growth of a small town where T represents the years since 1990, and they give you the function P equals 5,000 parentheses 1.05 to the power T. Which graph best models this function? So now would be the opportunity to use your calculator on your computers to plug in this function here, remembering that P will be where our f of x is, and you'll plug in everything after the equal sign there into your calculator here. Also, taking note at what type of function it is can help you to eliminate which graphs you can get rid of here. One other hint here is that when you're doing these graphs here, it's important to know that you're going to have to change the windows for these graphs. So when we're talking about changing the windows, right, we want our x mins and our x max to match what we have on the graph here. So our window for this graph here, if we take a look, all of our x minimums would be about 0 and the maximum all the way up to 24. If you want to go a little bit below these numbers, so say -2 or 30, that's also fine as well. Then our y min, again, we have at 0, but our y max, in order to see these graphs, if you take a look, all of them go up to 20,000. So that is what you need to put in your graph if you would like to see it on your calculator. After you do that, pick which one looks the closest. So again, you can pause it here and then give it a shot. This third one I'm just going to read through. It says Jordan jumps on a trampoline that is 1 foot from the ground. Which graph models the relationship between the height of Jordan's feet are off the ground in feet and the time in seconds that he jumps on the trampoline? So take a look and try and figure out which graph would make most sense to talk about Jordan's distance from the ground, his height from the ground, in terms of time, as we look at each one here. Taking a look at question 4, it says Miss Woods left work to drive home. On her way home, she stopped to buy groceries. Then she stopped again to buy gas. Finally, she drove the rest of the way home. Sketch a graph that models the situation and explain what the line means. All right, so you have again time and distance from home. You're sketching a graph that shows this situation. This one here, if you are completing it in your workbook and you would like for us to see it, feel free to take a picture and then send it to us through Schoology there, and we can take a look at it. And then the last one has to do with a function that should look familiar here, and it has Marty jumps from a diving board 15 feet from the surface of the water in a pool. His height t seconds, which he reaches the water, is modeled by the equation below. So they give us h equals -0.5 t squared plus 0.5 t plus 15. Complete the table of values to show Marty's height in feet 0, 1, 2, and 3 seconds after jumping from the diving board. So if we take a look here again, we want to fill this in at 0, 1, 2, and 3 seconds. And then also graph this function on the coordinate plane for 0 to 8 seconds. So be sure to label each axis appropriately. So again, if you're talking about your table here, we have x. We want our domain, which is our time, to go from 0 all the way to 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is what you're going to type into your calculator, fill out your table, and then plot your graph there. If you have any questions, make sure that you're emailing us or messaging us through Schoology. And if you just have any things that you want to go over, please let us know. All right, and good luck.